Okay, here's another word problem. A thermometer is removed from a room where the air temperature is 70 degrees Fahrenheit to the outside where the temperature is 10 degrees Fahrenheit. After a half minute, the temperature reads 50 degrees Fahrenheit. What is the reading at time equals 1 minute? How long will it take for the thermostat to reach 15 degrees? Okay. So, this is the same form as all the other word problems we've been doing. You have how long will it take? So you have a rate of changing temperature. A thermostat is removed from a room where the air is 70 degrees to outside where it's 10 degrees. After some time, 0.5 minutes, there's a temperature change. So that's a rate, but it's not the instantaneous rate. What is the reading at t equals 1 minute? How long will it take for the thermostat to reach 15 degrees Fahrenheit? Well, if you know the rate, you can know that. So you could write that the rate, the change in temperature, divided by the change in time, as time goes infinitesimally small, will give you an instantaneous rate, is proportional to the change in temperature, right? If you take something that's 10 degrees and you put it into an oven that's 1000 degrees, that thing is going to change its temperature quickly. You might put it in there only for 5 minutes and you take it out, that thing is real hot. Or imagine if you put it into a 5000 degree oven. So it's proportional to the difference between the two temperatures. The temperature of the object, here the temperature is 70 degrees where in the room, and then you're taking that thing into the room from the room and putting it outside where it's 10 degrees. So that's the difference. So you can tell that they're proportional. The rate is proportional to the difference in temperature between the two bodies. So this is the same formula we've been working with. And then to make this an equal sign, you have dt little t equals k delta t. But what's delta t? The change in t is just the temperature of the object minus the temperature of the surrounding. And we'll just leave this as t. T is a function of t. So, this changes, right? This changes. So, here, let me write this better. So we have dt equals k t minus tm. This is your delta t. So the temperature of the object here is you're taking this object, which is 70 degrees Fahrenheit, and you're moving it outside where it's 10 degrees Fahrenheit. So the temperature at time 0, T temperature 0 equals what? 70 degrees. Right. So this can be rewritten as dt equals k t as a function of time, because it's going to be variable. So this is a dependent variable. T is the independent variable. You can plug anything you want for t. But this is a dependent variable. T is a function of little t. And what's this? This is a constant. And what's the constant? 10 degrees Fahrenheit. It's 10 degrees Fahrenheit outside. And you put this object that at T equals 0, initially it is 70 degrees Fahrenheit. But that changes, but this doesn't change. Can you see that this changes? After 1 minute, it's going to be less hot, or less hot. It's going to decrease and decrease until it finally gets to this value. So that makes sense? So that's kind of the setup right there. So now what do you do? Just look at what you do now. So having understand that, we'll just rewrite that last part here. We want to do separation of variables, right? That's what we've been doing. You want to solve this differential equation is what you want to do. This is a first order linear differential, ordinary differential equation. And we want to separate the variables. So we got big T, little t. So there's two variables. Get those on the opposite sides of each other. So bring this down. So we got dt over d, the infinitesimally small change in temperature, and then divided by temperature minus 10. We'll get rid of this little t just to make it less messy. So equals k dt. What's that? Those are separated variables. Here you got little t. That's it. Here you got big t's. That's it. Now you're going to integrate those. Put the little integration symbol there. So what's this going to equal? This is going to be log, natural log, t minus 10 equals k t plus the constant of integration. Now what do you do? It's the same thing we've been doing. You use e. Now that's going to be t minus 10 equals e to the kt plus c, which just equals e to the kt times e to the c, which just equals e to the e to the kt times the constant. So let's write that final thing down there. So t is a function of time equals e to the kt c plus 10. There's your generic equation. But we need to solve for k and c. So what can we say? How can we get that k and c? We need to get that k and that c. That'll make it a proper equation. This is more of a general equation. So what do we know? Well, we know that at t equals 0, t is a function of t equals, what was it right at the beginning? Well, this object was in a 70-degree room. So that's how much that's the heat of this object, 70 degrees. Then it was moved to the outdoors, which was 10 degrees. But at 0, at the beginning of this experiment, at little t equals 0, you have 70 degrees Fahrenheit. See that? So what can you do now? Well, this is t sub t. I mean t given big T given little t. That's going to be equal to right here, 70 equals c times e to the k times 0 plus 10. What's anything times 0? That just goes to 0. What's anything raised